You know that gorgeous, super vibrant OLED screen on your phone or your TV? It is an absolute marvel of engineering. But it has a mortal enemy, an invisible threat that's, well, it's all around us, all the time, constantly trying to destroy it from the inside out. So let's dive into the incredible story of the invisible armor that protects it. So what do you think it is? I mean, really, what is the single biggest threat to those perfect blacks and those incredible colors? Is it, I don't know, dropping it on the floor? Maybe a scratch from the keys in your pocket? Nope, it's none of those. The biggest enemy is just water. And I'm not talking about dropping your phone in a puddle. I mean the tiny, invisible molecules of water vapor that are in the air we're breathing right now. H2O is the villain of our story today.
To really get a handle on just how big this problem is, you have to see what happens when an OLED screen is left totally unprotected. The effect is, well, it's shockingly fast, and it is absolutely devastating.
Okay, so this is what happens when you just expose the raw light-emitting layers to the atmosphere. Within just 30 minutes, you can actually see these dark spots starting to form. An hour later, they're getting bigger, they're merging together, and in only 2 hours, almost a third of the entire screen is just gone, dead. So what is actually going on here? Well, those dark spots are places where moisture has snuck into the screen and kicked off a destructive chemical reaction. It actually corrodes the delicate cathode and those organic layers that create light. In simple terms, water is literally rusting your screen at a microscopic level.
All right, so the problem is crystal clear. You got to keep the water out. Sounds simple, right? Well, it turns out solving this led to one of the most extreme engineering challenges in all of modern electronics. The level of protection they needed to achieve it's almost unimaginable.
To measure this stuff, engineers use a metric called the water vapor transmission rate, or WVTR. It's a pretty simple idea, really. How much water vapor, by weight, can pass through 1 square meter of a material over a 24-hour period. And obviously, when you're trying to waterproof something, the lower this number is, the better. And this is the magic number. The target WVTR for an OLED screen is 10 to the minus 6 grams per square meter per day. That's 1/1,000,000th of a gram. Just let that sink in for a second. We're talking about a level of impermeability that was, for a very long time, pretty much considered theoretical. Now this is what I find so fascinating. Putting it in context. A solar cell, something that sits outside in the rain, needs a WTR of about 10 to the minus 1. An LCD screen needs protection at the 10 to the minus 3 level. But in OLED, it needs a barrier 1,000 times more effective than an LCD. This isn't just a small improvement, it's a completely different universe of engineering. And this quote just brilliantly illustrates how insane that target really was. The goal was so extreme that the standard equipment, the tools they used to measure water permeability, literally couldn't detect it. They were aiming for a target that was completely off the charts of their own measuring tools. So how on earth did they even start to solve this? Well, the first solutions were pretty clever, actually, and they took inspiration from something we're all familiar with, food packaging. The idea was simple. If you can't build a totally perfect wall, just put something inside the box to mop up whatever manages to sneak through. The two main early methods were the edge seal and the frit seal. You can think of the edge seal like a tiny Tupperware container. It uses a line of epoxy around the edge, and it has a little moisture-absorbing packet called a desiccant tucked inside to trap any stray water. The frit seal was way more advanced. It used a special glass paste that's melted with a laser to create a perfect hermetic weld. No desiccant needed because the seal itself was basically flawless glass. And here's how that edge seal process actually worked. You'd start with a glass cap, stick that desiccant tape on the inside, and then run a little bead of epoxy all around the edge. Then you'd place this whole thing onto the OLED panel inside a completely moisture-free nitrogen environment, and then zap it with UV light to cure the epoxy. It was a really reliable method, but that internal cavity and a little packet made the final product kind of bulky. And that bulkiness? Yeah, that became a huge problem. As we all started wanting bigger TVs and thinner phones and even curved screens, these early cavity methods just couldn't keep up. That empty space on the inside made large screens really fragile and thick. Engineers needed a completely new approach. This table here gives us a fantastic roadmap of how this whole thing evolved. We've talked about the early cavity methods. Now we're entering the no-cavity era. And this is where things get really cool, with tech like dam and fill and face seal paving the way for the big, thin screens we have now, and eventually leading us to the holy grail, thin film encapsulation, or TFE. So the core innovation here was brilliantly simple. Just get rid of the empty space. By filling that gap between the OLED layer and the cover glass with a special resin or an adhesive film, the whole structure becomes solid. This stops it from flexing and is what makes those huge, beautiful screens possible.
A really popular way to do this is called dam and fill. You literally build a thick dam of resin around the edge of the panel, then you pour a thinner, more liquid resin into the middle. When you press the cover glass on top, that liquid fills every single tiny void. But, and this is the catch, that resin still isn't a perfect moisture barrier. So this whole trick only works if you first add another super thin protective coating directly onto the OLED itself. That's called a passivation layer.
But hey, even filling the gap wasn't the final answer. For the truly futuristic displays, the ones you can fold up and put in your pocket or roll up like a newspaper, you have to get rid of that rigid cover glass completely. And this brings us to the amazing world of thin film encapsulation.
The goal here is pretty radical. Instead of putting the OLED inside a protective box, TFE is all about making the protection itself an invisible, flexible, microscopic part of the screen. No glass cap, no metal foil, just a series of impossibly thin layers.
The basic building block of TFE is something called a dyad. And that's just a fancy word for one pair of two different layers. First, you have a hard, inorganic layer that acts as the main moisture barrier. And second, you've got a softer, organic layer that acts kind of like a coat of varnish, smoothing everything out and covering any tiny little flaws in that first layer. So you're probably asking, why not just use one really thick barrier layer and call it a day? Well, the problem is that at this tiny microscopic scale, any single layer is basically guaranteed to have tiny, unavoidable defects, little pinholes that a water molecule could easily just sneak right through. And this is where the real genius of TFE comes into play. Engineers created what they call a tortuous path. Okay, picture a single water molecule finding a pinhole in that first barrier. It gets through, but then it hits that smooth organic layer, which forces it to travel sideways. To keep going, it now has to find another pinhole in the next inorganic barrier, but because it had to travel sideways, the second pinhole is nowhere near the first one. By stacking 3, 4, or even 5 of these pairs, you create a microscopic maze that is so complex that the path for a water molecule becomes incredibly long. It effectively blocks it out. And that, right there, is the breakthrough. This invisible, multi-layered armor is what finally made the dream of flexible electronics a reality. It provides that impossible 10 to the minus 6 level of protection, but without any of the stiffness of glass or metal. So an epic, decades-long battle against a single, invisible molecule is the entire reason we have the incredible display technology that we have today. It's an amazing journey, from bulky little cans to microscopic mazes. It really makes you wonder, what other seemingly simple challenges are engineers battling right now that will completely redefine the technology we all use tomorrow?